So in today's lesson, we are going to learn how to work with solids of revolution. So we've talked a lot about this shape here. So we know how to find the area under the curve between those two starting and stopping points. So we're able to integrate that. But one of the things that we're going to do is we're going to take that shape and we are going to revolve it about the x-axis. So we're going to go 360 degrees about the x-axis. So think about this shape. So what would this shape look like when we rotate it about the x-axis? So this here is going to keep going all the way around. So think about what that shape would be. Sometimes that's the hard part about it, is actually what the shape is. So if I rotated that all the way about the x-axis, I get this shape. So you can think about it like if you can turn your head sideways. See how it kind of looks like a vase? But the thing is, it's a solid. Everything is filled in there because this whole shape is rotating around. And since that whole shape is rotating around, we get this filled in vase. So it's completely solid. That's why it's called a solid of revolution. So what we're going to learn how to do is we're going to learn how to find the volume of that. So we're going to be able to figure out what is the volume of these three-dimensional shapes just based on knowing what its 2D shape is. So just based on this. Okay, so if we rotate that 360 degrees about the x-axis, the shape becomes a solid of revolution. So what shapes are within that solid? So I know I talked about like that whole shape is like a vase, but what are all of the shapes that we compact together onto itself? So like think about when we were using these, what shape were we making here when we were finding the volume? We were doing rectangles, right? We were finding the area of rectangles, but then what we ended up doing is we were making those widths infinitesimally small. So therefore that width was like nothing, and all we had to do then was find the vertical heights of these. It's exactly what we're doing here, but now because it's a 3D solid, I can't just draw vertical lines. That's not what my shape is. So the shape of it that we're looking at is actually the shapes themselves are actually cylinders. But then what's happening, so I can find this whole cylinder. But then what we're trying to do is we're trying to make this infinitesimally small. So the shapes within the solid are cylinders. But then what we're doing is since we're making that horizontal piece so incredibly tiny, so this horizontal piece so incredibly tiny, that what we're actually doing is we are finding the volumes, we're finding the areas of circles because we make that, so like here's a cylinder, right? So think about this now turned sideways on my shape. What I'm trying to do is I'm trying to make this super, super small because they're not vertical. They're curved some sort. So I'm going to have error. So I could end up doing this one with circles on each end, which is the cylinder. So what we're trying to do is we're trying to make those heights super close. But no matter what, how do you find the volume of a cylinder? Volume equals area of the base, circles pi r squared times its height. So that's how we find the volume of a cylinder. But again, we want that height to be pretty much nothing. So when we find the volume, we're looking at the limit as h approaches 0. Limit being what happens as it gets super, super close. From A to B, those are the endpoints. So that's like from here to here. So the formula is pi radius squared times h. Think of the radius. The radius is that. So think about what that radius means. The radius is half of the vertical distance. So therefore, the radius is from the x-axis to my function. It's the height of my function. That would be y. It's the output. It's the output, no matter where my input is. So if I put in an input of, say, 7, I put 7 into my function, it gives me the height at 7. So this part right here is therefore the y value, which we're going to call f of x, just to keep our notation nice. And then it's pi times the radius squared times h. So that's what we're looking at, is we're adding up all of those areas. We're adding up all of the areas of those circles, which are really miniature cylinders, when we make our height approach 0. Therefore, we are going to integrate from a to b. I'm going to pull that pi out because pi is just a numerical value. I'll do that in just a minute, but for right now, we'll leave the pi in there. And then it's f of x, my y value, squared with respect to x. So you'll notice h approached 0, so therefore we dropped our h out of there. So this is equivalent to the integral of a to b, pi outside, sorry. So pi times the integral from a to b of whatever my f of x is. If you just want to put y in there, that's perfectly fine, squared with respect to x. Odd because I said with respect to x, but then here I went and used a y. Keep in mind, this is going to be my function, whatever my function happens to be. So if it was 2x plus 5, if it was a linear equation, 2x plus 5, 2x plus 5 go in place of this. So this will find the volume of a three-dimensional figure that is found by revolving a two-dimensional figure about the x-axis, as long as it touches that x-axis. Okay. And we're going to have a second part later on where it's not going to be completely in touch with the x-axis. We'll have to take that in consideration. But that's our next video. So what we're going to do is we are going to use integration to find the volume of this solid generated on the line y equals x. So nice basic linear equation from 1 to 4. So this is at 1, and then it stops at 4. And that's revolving around the x-axis. Again, this is a solid figure. So to find my volume, we just talked about here, this is kind of like a general formula for finding the volume of revolution. So we put that pi on the outside. I know you guys aren't all putting your numerical values outside your integral. I highly recommend it. It just makes your math a little bit easier. And then sometimes you'll realize you don't have to do u substitution because some of you are trying to do u substitution. Okay, so volume equals pi integral. I'm going from 1 to 4. My function is x squared dx because my function is just x. So therefore, when I integrate this, I get pi times x cubed over 3 from 1 to 4. And then I need to substitute those values in, so that's pi times 4 to the third, which is 64 thirds, minus 1 third. So 64 thirds minus 1 third is 63 thirds, and 63 thirds is 21. We attach that pi. We are doing volume, so this is units cubed. Okay, so we're thinking about the cylinders. We're making those heights approximate 0. We're taking the limit as h approaches 0, which means we're finding the areas of circles. We're adding all those circles up that fit in there. And in order to do those circles, I need my radius. Fortunately, my radius is just the distance from x to that function. Therefore, every one of those y values, the heights, because again, it goes to the x-axis, are based on your function. Okay. Oh, one other thing. What I could do is I could check this geometrically, because if I actually continued this here, and if I instead went from 0 to 4, what I'd end up having is a cone. And you can find the volume of a cone, and then so find the volume of the whole cone, find the volume of the little cone, and subtract them. It's just a truncated cone. So that's how you could check it geometrically, just to make sure that, yes, you are right. Okay. Totally weird function. No idea what this looks like. It's rotated 360 degrees about the x-axis. Find the exact volume of the solid generated. Okay, so we have to go on blind understanding of what we're doing, not just being able to pictorially think this through. So I know to find the volume equals pi times the integral 0 to pi over 2. And then it's the radius squared. So this is the height at any point along the way. So this is going to be my radius. And then I have to square it. And that is with respect to x. Okay, so that's the setup. Just simplifying it here real quick. So this is pi integral 0 to pi over 2. This is the sine of 2x dx. So now you just have to integrate the sine of 2x dx. So now you got to go back to integration rules. And that's really the part that starts to get a little bit more difficult with these problems, is just remembering what do you know about this stuff. So therefore, integrating the sine of 2x. So this is going to give me pi times derivative of sine of x. That's just a linear piece in here, no big deal. So the derivative of sine of x is the negative cosine of x, but that's my linear. But then I have to undo this multiplying by 2, because then when I take the derivative of it, I get a 2. Therefore, I have to divide out that 2. And then this is from 0 to pi over 2. Okay. I'm going to pull out the rest of my numbers before I actually substitute these in. Just, again, trying to make it a little bit cleaner. So I'll pull out the negative. So this is negative pi over 2 times the cosine of 2x from 0 to pi over 2. So therefore, it's negative pi over 2 times. It's going to be multiplied by the whole thing. And this is why pulling those constant terms out is super beneficial, because now I just have to do the cosine, ooh, that's x, of 2 times pi over 2 minus the cosine of 2 times 0. Thinking about this, so this is just pi. So therefore, at pi, cosine at pi is my horizontal, so that's negative 1. And the cosine at 0 is positive 1, which means this is negative pi over 2 times negative 2, which means my volume is pi units cubed. So there's just so much that we can throw at you in a problem. So we're looking at volumes of revolution. You needed to know how to integrate a trig function that had a multiplier of 2. It's just a linear function in that trig function, so no big deal, no u substitution needed. And then being able to break it down, and then being able to apply trig and what you know. What is the cosine of pi over 2? What is the cosine of 2? What is, well, that doesn't exist. What is the cosine of each of the values along the way? Okay, last example is the following. Find the volume of the solid formed when the graph of the function y equals x squared for x is greater than or equal to 0 but less than or equal to 5. That's revolved around the x-axis. So this one, you could graph this so you have an idea of what it looks like. So parabola through the origin, and I'm going from 0 to 5, and I'm finding this shape in there that's revolving around. So therefore, I get fancy here. So we're looking at this shape that we end up getting three-dimensionally. Kind of looks like an ice cream cone. Kind of. A little different, but. Okay, so integrating this. The volume is pi times the integral from 0 to 5. My function, which is x squared, my radius, that is squared with respect to x, because remember, it's radius squared. That's pi times the integral from 0 to 5 of x to the 4th dx, which is pi, integrating. Questions? Not that you could ask me, unless you email me. Okay, so therefore we get pi times 5 to the 5th over 5 minus 0 to the 5th over 5, which just gives you 5 to the 4th times pi. So therefore that is 625 pi units cubed. Okay, So now you're going to practice these types of problems. Try to be as comfortable as you can. Again, remembering that now instead of finding the areas of rectangles as my h approaches 0, we are now finding the area of cylinders, or the volume of cylinders, as h approaches 0, which means we're finding the area of a circle, and we're adding all those up. Okay, fantastic, guys.